AS table. You'll use an AS table when you need the final concentration of a shift. Gotta go back the other way. So this is going to go down by x. That's going to go up by 4x, right? 1 to 4 ratio, and this is going to go up by x. So at equilibrium, it's going to be x for that, 0.74 plus 4x for that, and then 0.01 minus x for that. Are you with me on this? Okay. You have to do some of these problems on your own. The solution guide, I believe, in every case is going to do this. It's going to take the reaction all the way in the favorable and then have it drift back, just like I'm talking about. Okay? So please do try that.
Is it all equal K?
Yep. So yeah, we're going to have the normal K. K equals, and that's that K, 1 times 10 to the 30th.
Or just 10 to
Or what?
30. Or it's just 30.
It's just 30.
It's not 30.
So we have products, which is 0.01 minus x over reactants, x times 0.74 plus 4x raised to the 4th power. Is x big or small as it's going to the left? It's ridiculously small. So that's not going to change the 0.01. I can neglect this. And it's not going to change the 0.74. 0.74 plus 4 times a minuscule number is still going to be 0.74. So that's gone. Now the math is so easy. Because you only have one x term in there. Unfortunately, it's in the denominator. Don't leave it down in the denominator. But I trust that you're not going to do that. It's 0.01 divided by k divided by 0.74 to the 4th. Anybody feel like yelling out their answer?
3.3 times 10 to the negative 32.
There it is. Yep. This is the concentration of the mercury ion at equilibrium. So, man, just an extremely trace amount of the mercury ion. Is there some there? Yeah, I guess. Maybe one ion in a swimming pool kind of thing. But there's some. Now, you might wonder, why did we have to do that whole modified ice table? Couldn't we just shift one way and have it good? I'll show you what it looks like if we did that. If we were to just take this to the right, we started with, let me just write it up here, Hg plus 2 plus 4 iodide ions yields HgI4 with a negative 2. Okay, and we know what the K value is. So if we start with 0.01 and 0.78 and 0 of that, if we're just going to do our ice table and just be bulldogs about this thing, we're going to say, okay, ice. This goes down by x, this goes down by 4x, and that goes up by x, right? And so at equilibrium, this is 0.01 minus x, this is 0.78 minus 4x, and this is x. Okay, looks fair enough. The K value is 1 times 10 to the 30th. Oops. And that's equal to products, x, over reactants. 0.01 minus x times 0.78 minus 4x quantity to the 4th. X is very close to 0.01, so you can't neglect it there, and you can't neglect it there. So you're going to wind up with a 5th order polynomial that you have to solve. And figure out which of the roots is going to fit this one. Can you do that on your calculator? You probably could if you graphed it and looked for the zeros. So you probably could do that. And if that's easier for you to do, then maybe you would just want to do that. Oh, you can't even zoom in that far on it?
Oh, yeah.
Yeah.
How come you can, or how come you can't neglect the X there on the denominator?
That one?
Yeah, let's do X.
Yeah.
Well, because X, this is our limiting reagent. This is, yeah, this is going to be very close to 0, right? Yeah, at equilibrium, this is going to be very close to 0. So if you say, remember, we only neglect X when X is so small that it doesn't really affect the value of it. So the minus X term is very big compared to 0.01. It's almost 0.01. So you can't neglect it. You only neglect X when it doesn't really change its value. Now over here, you can make an argument that, oh, hold on a second. If we neglect the X here, because X can't be any bigger than 0.01, right? That's as big as that number is. I don't even think it would give you that number. Even if you graph this thing, by neglecting that minus 4x, you wouldn't even be close to that. So it may be impossible to do without just doing that technique of going all the way over and then have it come back to equilibrium. So that's why we have to do that technique. Now, of course, there are plenty of problems like that in the problems. I don't know about plenty, but there are some. So when you want a concentration of something after a shift in the equilibrium, that's when you need to use that OS table. Nabil.
Does 100 milliliters of solution not matter? Doesn't matter.
It does not matter. Yep. If it asked you for moles of something, then the volume would matter. Otherwise, it doesn't matter. Anything else? Ooh, man, this is hard. I told you, this is a hard chapter.
Just more at the end of
Yeah, one from this.
Yeah, go to the camera so you know like
Yeah, like
high five the camera.
Somebody come finish the vlog. It's not going to be me.
Oh, no,
No, we got.
Don't.
Wait, go back a little bit more. Go back. Okay, good. Wait, over there.
That's the end of the vlog today with Chem Daddy. See you guys next time.
Oh, yeah.